This video is brought to you by Vita Bee Health. Thanks Vita for sponsoring this channel. Please check them out, link in the description of this video. Hello everyone, today I'm pleased to have Dr. Frank Rinkevich joining us once again. Frank is a research entomologist with extensive training in insect toxicology at the USDA in Baton Rouge, and join us today to update us regarding his research on Amitraz-resistant mites, a topic that we covered here many times in the past, and it is a concern of many beekeepers out there. This podcast was recorded a couple months ago, and I had some sound difficulties that I could resolve just now. I almost lost this interview because of technical problems here, and I'm so glad that I could recover. In this episode, we will also discuss selection for Varroa-sensitive hygiene bees and other topics. And now, I introduce to you Dr. Frank Rinkevich. All right, Frank, welcome back to the show. It is a pleasure to have you back. How are you, my friend?
I'm doing very, very well. It's queen season down here at the lab, so we got about 200 nukes that we just made up. We're installing cells, getting queens ready for the big season, doing a lot of Varroa testing, obviously, this year, but also working on people to do their own selections for Varroa-sensitive hygiene in their own stock. So I'll be taking this show on the road pretty much all summer long to do this field research where we'll be working directly with beekeepers. So it's busy time right now, so it's exciting.
Good. Always busy, always good. I want to start this conversation, Frank, asking you to give a little overview about everything you found so far with Amitraz resistance, which is the project that you were working for I don't know how many years right now. And before we jump into the main topic of this conversation, which is your last publication about the different variables that was affecting the Amitraz resistant testing that you developed at the Baton Rouge lab. Can you give us a little overview about where we are, what the project is, where we are, and where we're going with that before we jump into the details here?
Yeah, very well. So this project started in 2019, just hearing some conversation with beekeepers who kept on saying, Amitraz doesn't work like it used to. We'll treat 30 colonies in the apiary, and the treatment works great on 25 of them. And then there's 5 colonies that still have high levels of mites, even though they've been treated just the same. And so when I started hearing some explanations of why it's not working, the only thing I came to the conclusion was that it had to be resistance. So my background is in insecticide resistance. So this was a nice meeting of a need by the industry and my background, my training throughout my PhD. So in 2019, we developed the test for Amitraz resistance. And so we started this by using Varroa mites from our lab. We don't treat for Varroa mites at the lab unless it's part of an experiment. And so we knew we had a susceptible population. Whenever you're doing any kind of these resistance tests, you have to make sure you have the right susceptible population. So that way you're comparing susceptible to resistant and not resistance to resistance. And that's difficult because as we've been finding out, there's a lot of resistance out there. But because of that setup we had at the lab, we knew that our population was susceptible. So what we did is 2 different things. We established the LC50 to technical grade Amitraz. So this is not any kind of strip, not any kind of colony level treatment, just pure Amitraz. When we expose the Varroa mites to different concentrations, we could determine the LC50. That just means that's the concentration that will kill 50% of the mites. Or in other words, an individual has a 50-50 chance of dying when exposed. So once we did that, we established that this population is susceptible. And then we also compared that to the Amitraz resistance test that we do in the field. We'll go around with the containers with the square of Apivar in them. And then since Apivar is formulated at 3.3%, concentration is the same, we have to use time as our variable. So we found that in our susceptible mite population, it took 3 hours to knock all the mites off the bees. Therefore, if the mites are still on the bees after that 3 hours, we know by definition, those are resistant Varroa. And what we did is then we tested a bunch of different populations across the country. In 2019, we did a road trip from Louisiana up to New York and then out to the Dakotas. And we found that Varroa populations that were more resistant in the cup test when exposed to Apivar had a significantly higher LC50 to Amitraz. So therefore, we could connect those 2 things, the LC50 and the results of the resistance test that told us the same thing. that the reduced apivar efficacy or higher Amitraz resistance was due to insensitivity to Amitraz. So we established that physiological link 5 years ago. Well, then when we're doing this test, as a toxicologist, you're always thinking about the ways that your setup might be wrong. Typically, when we do these tests in the lab, we have very highly controlled conditions. But as you know, working with bees, especially in the Dakotas, some days it's 82 degrees and other days it's 50 degrees and cold. So when I was thinking about that, I said temperature might be important here, but we had no data on how temperature affects Amitraz resistance. And that's where we went into this experiment, because we had this data from the last 5 years and we had to make sure that it was the data was correct. And what we've been finding over the past 5 years is that we keep sampling more and more colonies every year. I think the data set that we're going to publish this year has 1,656 colonies in it. So it's a pretty wide survey of Amitraz resistance. And what we've been finding over the last 3 years is that we have been seeing an increasing trend of Amitraz resistance levels. It gets higher and higher every year. Now, I don't know if that trend is absolutely real, because we do see this trend to increasing resistance. We don't know if that trend is real, or maybe we're just working with those people who want us to work with them because they have no issues. So maybe we're biasing our sampling in some way. So with that in mind, we really need to do more passive sampling. So just getting in samples, whether or not people are reporting resistance problems or treatment failures. So that way we get kind of the background, kind of a wider survey. So that way we're not biasing our samples. So as I mentioned before, we ought to find about temperature. And with Amitraz, going into literature, there was some evidence to say that it might be temperature-dependent toxicity in other organisms. So I thought, well, Varroa shouldn't be any different. So what we did was we did the Amitraz LC50 test at a bunch of different temperatures from 10 degrees up to 35 degrees. And then we also did the Amitraz resistance test in the cups at those same temperatures. And what we found is in the Amitraz resistance test in the cup, at high temperatures, we got all the mites to fall off without any apivar. So under control conditions, when it was very hot, above 30 degrees Celsius, mites just fall off the bees on their own, whether they're resistant to Amitraz or not. So under control conditions, mites fall off bees when it's hot. And we've known about that for a long time. I mean, go back in literature, 20 years ago, people were talking about that. And there's been some devices that use that thermal intolerance of Varroa for treatments. There are these bee saunas, and Zach Wing had the hive, the frame that would turn on and get high temperatures to kill the mites. So we know that temperature affects Varroa. However, at those high temperatures, when the Varroa fall off on their own, that could actually lead us to underestimate resistance, because genetically resistant mites might be falling off the bees at those high temperatures due to temperature, not due to Amitraz, but due to temperature. So we could get genetically resistant mites to appear susceptible in our test due to temperature. So when I found that out, we went back and had to reevaluate our data. So when we compared the genetics, compared that to the resistance levels that we've been finding in the field, we found that we've been underestimating resistance by about 25%.
25.
Yeah. So when we've been looking at it, about half the mice that appear susceptible in the test are actually genetically resistant. So therefore,
Wait. That's a lot.
I know. And that's what was really frustrating to me, is that I wanted that test to be like more clean. So when it comes to susceptible, we could kind of get that picture. But however, when we run the test for resistance, if they're resistant in the test, they're almost always resistant genetics. So the resistance test that we've been running in the field is I'm calling a conservative measure of Amitraz resistance, because we've been finding about 30% resistance in the test leads to treatment failure. But I think that now with the genetic information, I think about half those at 30% resistance level at the treatment level in our test, it seems to be associated with higher levels of actually genetically resistant mites. So that's kind of what I'm thinking about, is perhaps we've been underestimating resistance for a while based on these findings that we found with temperature. So that's what we found at high temperatures, right? So at high temperatures, mites fall off the bees. At low temperatures, though, Amitraz toxicity goes down. So when we run the resistance test, fewer mites fall off the bees. Okay? So therefore, that might give the appearance that those mites are resistant. Because what we found is at low temperatures, Amitraz is less toxic.
Do you think this because that limits the bees to walk faster and it spread the compounds, and that would be affected? What do you associate the low effect of Amitraz and low temperatures?
So that was definitely one of the things that we talked about, was maybe the bees just kind of cluster on that square and don't move around and doesn't distribute it. Well, what we did was when we then took those mites and exposed them to pure technical grade Amitraz at low temperatures. And sure enough, at lower temperatures, the toxicity to pure technical grade Amitraz was also lower.
Oh.
So yeah, so it's not the bees' movement. It has to be that the Amitraz is less toxic at low temperatures. Whether it's the glass vial bioassays that we do for the LC50s or in the Amitraz resistance test in the cups. So that was the mechanism.
Do you have any reason to why?
Yeah, I think that it's pretty clear that Amitraz actually isn't what's killing the mites. It's that Amitraz is actually what we call a pro-miticide, meaning it needs to be converted into something else to actually kill the mites. So Amitraz needs to be converted to this molecule called, let me just say this real quick, N2,4-dimethylphenyl N-methylformamidine, or as commonly known as DMPF. So DMPF is a breakdown molecule of Amitraz. That is what actually kills the mites. So we did that bioassay in the lab. We compared toxicity of Amitraz to DMPF, and the toxicity is the same. Therefore, we know Amitraz needs to be converted into DMPF to kill mites. And that's kind of common actually in the insecticide world. There's many things that many insecticides that need to be converted into something else in order to become toxic. So the organophosphate insecticides, specifically with honeybees, we think about Coumaphos, right? Coumaphos needs to be converted to the oxon form, which means it's metabolized and it replaces a sulfur with an oxygen, and that's actually what kills the Varroa. So this is kind of common in the miticide insecticide world, believe it or not. And I think that at low temperatures, the metabolism of the mites is reduced, and therefore the conversion or the activation of Amitraz into DMPF is also reduced.
So nothing related with the bees or the mites themselves. You think it's the chemical activation of the compound itself with the temperature?
Yeah, I definitely think it's the temperature that's influencing the activation rate. And that's kind of what we see across the board. That's what we call a temperature coefficient when we're talking about toxicity. Because if you lower temperature and toxicity goes down, like in this case, that means it's not being activated. That's usually indicative of a pro-insecticide. Conversely, if you reduce temperature and toxicity went up, that will mean metabolic rate is down, and therefore you're not detoxifying. So it's kind of two sides of the same coin. Yeah. So whether the toxicity changes with temperature, whether that's a positive relationship or a negative relationship, it tells you about the potential for those compounds to need to be activated.
Okay. The question that's going to come to me all the time, I'm going to let you answer directly from the source. How that help beekeepers? The research itself.
So I think that's really interesting because with this, so what's really important to understand here is that, yes, Amitraz does break down, right? When we look at Amitraz levels in a colony for doing pesticide residue testing, we almost never look for Amitraz because it's almost always converted into DMPF. So yes, Amitraz is breaking down, but what it breaks down to is something that is toxic. And so with that in mind, in this paper, we also looked at something like that, where we looked at very old strips of Apivar. So I had some strips of Apivar that I got that were manufactured in 2014. So when I did the test, they were over 8 years old. And what we found was that regardless of manufacturing date or how old those strips were, they seemed to really knock the Varroa mites off of mice susceptible Varroa. So therefore, we know that, yes, Amitraz is breaking down, but it's breaking down to something that's toxic. And that's kind of what we saw with those old Apivar strips still being effective as having comparable efficacy as new strips.
That fits a lot with, in Florida, I have several commercial beekeepers, they could swear to God to me that they think that the strips work better if you keep it there longer in the hives. If in the first 2 weeks when they put the brand new ones, they said sometimes it doesn't work for whatever reason, but sometimes they forget the strips over there. And then we realize the old strippers or the strippers that stayed longer there, that's for the time that things start to work. So do you think that could be related with that? Depending on the batch of the Amitraz and the strips, they do not convert at the beginning and might convert a little later, or depending on the environmental conditions, that could be the activation point to get a better result.
Yeah, so Apivar, as it's formulated, it will not provide that very rapid knockdown that we're all looking for, right? We want to put those strips in and start to see mites dropping. Unfortunately, when applied at the colony level, it's just never going to activate and knock mites off very rapidly. It does take time. That's why on the label it says it's a 6-week treatment interval. So that's why we have to wait until the end of there to start to see those results. And that's just the nature of the Amitraz when applied to colony, at the way that Apivar is formulated. So the longer those strips are left in up to that, and according to label at that 6-week interval, is probably the time. So you have to wait instead of just put a strip and then look after a week. It'll take a while.
Let me rephrase myself. Yes, what they mentioned was need to be at least almost double what the label were saying to work for them in Florida for whatever reason. That's what I meant.
Yeah, and I've heard very similar things from a lot of people, but I don't think it has anything to do with the rate of activation. I just think it's the way that the strips are formulated that it just takes a while for them to work. And I think they start to see those results after a longer period of time, just because, it's starting to hit all the mites that are coming out of the brood. You've gone through, let's say at the end of 6 weeks, that's 2 brood cycles. So you should have got most of the Varroa. And so if they are left in longer, maybe they're getting that third round of mites coming out of the brood cells. And that's been something that I know that people have been encouraging a longer treatment period, but the label still says 6 weeks.
6 weeks. Right. Yeah. All right. So Frank, again, how that's going to help the beekeepers? So you will answer that. Go ahead.
Yeah. So I think that the way it should help beekeepers is that they should have confidence in that the product has a consistent formulation that provides efficacy against Varroa mites when stored at the right conditions. So when I was using this Apivar in these tests, it was stored in my lab at the room temperature, right? So therefore, we know that if on susceptible mites, it'll knock them out. So therefore, I don't think compromised product is a reason for treatment failures. It could be due to underdosing, so label says 2 strips per 5 brood frames. And so that means potentially, in some cases, up to 4 strips per colony. And so that's the necessary and required treatment. If you put 1 strip in a 6 deep, that's definitely not going to get rid of your Varroa problems. So that could be a source of a treatment failure. But when used according to label, if the mites are susceptible, it should work as prescribed by the label. So, and the way that would help beekeepers is that if you're not seeing efficacy due to an Amitraz treatment, it's probably due to resistance. Therefore, probably use something else that's not Amitraz. And unfortunately, there are other products on the market that can be used that are not Amitraz based. So we have formic acid and oxalic acid products, and a number of other things that are still coming on the market now. However, the challenge is to find products that have consistent efficacy like Amitraz does on Amitraz susceptible populations. And, down here in Louisiana, formic acid is not usable for a good part of the year just because of the potential it has to damage brood and queens. However, if temperatures, in the temperature range as per the label, those materials should provide adequate Varroa control when used according to label. So that's what's really important here, is to understand what levels of Amitraz resistance you have in your population in order to avoid treating with something that's not going to work. Because let's face it, miticides aren't cheap, and no one likes to waste time and labor. Yep. So by knowing the resistance of your population, whether it's with the resistance test that we can do in the field or with genotyping, that could help save colonies that might be lost due to a treatment failure due to Amitraz resistance.
Fair enough. Frank, there is another way that we can deliver Amitraz. Do you think there is other ways that are more better? I consult for this company, and there is no sponsor, nothing related with that, but make a lot of sense for this discussion because they were kind of sublimating the Amitraz, and that means they're gonna heat it a little bit. It's gonna activate and gonna convert to DMPF a little bit more, and gonna go through different areas of the mites. I was wondering if you know, or if you know any test about other delivery methods of Amitraz.
Mm-hmm. Yeah, so vaporization is definitely something that they use over in Europe. Quite, I don't know how extensively, but I know it is a treatment option. I think the product's called Wall. I think that's what it's called, Wall. I think, I'm not sure. And that's a product where they heat it up and it volatilizes to a colony. And there's a company, I think they're from Israel, that has it's like a meter dose that they could apply Amitraz with a vapor. So vaporizing Amitraz is also another option. And when you look at vaporization, whether it's Amitraz or even oxalic acid, it's going to be administered to the bees at a much more rapid pace than it would be through a contact bioassay than with the strips. So typically with those vaporization or sublimation sort of things, it's going to deliver a rapid exposure. However, there's not going to be much of a residual. Once that vapor is gone, it's typically not going to provide any kind of residual treatment like a strip would, a strip treatment. So there are ways to do that might be a little bit more labor intensive, but will give also to potentially a faster knockdown with those vaporization methods.
Yeah, that's why I was encouraging to that exactly the Israeli company that you mentioned. The product is called Hive Master. It's a device, and they program the device to release the pulses of sublimation or vaporization of Amitraz at nighttime, specific bursts every night, for 6-7 days, and just to cover a good part of the brood cycle. And they got results, at least in the paper, that was very nice. And I said, okay, you want to real test it, give it to the commercial beekeepers in Florida. And some commercial guys come to me and said, that works. So, and then I was wondering, why can we, find a ways to do something similar? Or, because I remember when I look at it, there are people doing this from the 60s, from a long time ago, with the sublimation of Amitraz against mites. And I said, well, let me ask Frank about that. There's something new about it.
Yeah, and that's definitely something. And so it's going to provide a whole new route of exposure. So even though it's still Amitraz, it's going to give a different route of exposure. So it's going to be different than a contact that they would get from the strip. So what I think, so I just want to clarify something. Whenever I say I think, it's kind of my guess, my hypothesis.
Yeah.
And that's going to be not founded on data yet. When I say I know, or the data suggests, that means that there's actual literature. So in this case, I'm going to say, I think what happens is that volatilization or sublimation gives a much more rapid dose at a short period of time that's able to potentially overcome some of those the barriers that they could knock them down and get them under control, because it's just a much more rapid response, rapid administration. I still have to do some research on that, because that's always a question. What do we do with Amitraz resistant mites? Can we just apply more? Increase concentration? You could, but that's not going to last very long, because what's going to happen is you're just going to make your population more resistant over time. And so that's usually, I can ask beekeepers 3 questions, kind of have a good idea if I'm going to see resistance. 1, do you treat more frequently? 2, do you treat with higher intensity, more strips kind of thing? And if they say yes to both of those, it's a pretty good idea that they have resistance.
Bingo.
So, but I think that the trick here is to not just keep increasing the dose of Amitraz. I think the biggest thing we can do is to use other miticides, so do rotations. And this is something that we've seen in many other agricultural systems to overcome resistance. So hitting them with one, in our case, a miticide with one mode of action, and then following up with a miticide with another modes of action. So that way the mites are always guessing, anthropomorphizing it, their physiological systems won't be adapted to the materials that are being applied. So what that means is that either they might have resistance to Amitraz, they're probably still susceptible to oxalic acid, formic acid, thiamine, and all those other materials that are out there on the market. So that's why it's really important to kind of not allow them to develop tolerance to any one of those materials through rotations.
The other thing that just crossed my mind, I just want to say that before we move forward, about the sublimation or evaporation or whatever we call what's going on over there with the new delivery method of Amitraz, is that it might reach other, the respiratory system, right, of the mites, instead of just contact.
I would think so. I'm not sure, because with some of the volatile products that we had for example, I used to work on houseflies. Yeah, it would get into them through their breathing apparatus. I just don't know how that would work with Varroa mites. I would assume it would be similar, but not sure.
Yeah, just what I mentioned that. So now, okay, we have the system. You find a lot of variables in it. Just to how science works. You start to do one thing, and then things evolve to a different direction. You find other variables. I want to know what the project is going right now. You said you're going to start this season. So what's the season is all about?
So this season is, I'm going to establish a apiary where we have Amitraz resistant mites, because there's a lot of things that we need to do on how they behave at the colony level. Biggest thing that we have to find out is there a fitness cost to Amitraz resistance? So what that means is, if they're resistant to Amitraz, do they have compromised performance in other areas? So typically we see this sometimes, not all the times, sometimes when we have resistance, like with houseflies, if they're resistant to pyrethroids, they can't detect temperatures. Houseflies tend to prefer warm temperatures, but when they're resistant to pyrethroids, they can't detect temperatures. Pyrethroid-resistant aphids don't respond to alarm pheromone. So all these things add up to differential reproduction in the absence of insecticide. That's what's critically important here. So we have to figure that out, is what's going on with Amitraz resistant Varroa. And the reason why I'm really interested in that is that if there was a fitness cost, which there may be, that's why I think that we see fluctuations every year. So we don't see all these populations all becoming resistant all at once. So what that tells me is that probably over the wintertime, they might not overwinter very well. They might not reproduce as much. There's something that leads to a differential reproduction when Amitraz isn't around. So it provides good protection when Amitraz is there, but they're compromised in some way, potentially. So what we want to do this year is take Amitraz-resistant Varroa and put them in a colony with Amitraz-susceptible Varroa. And now that we have this genetic marker to test for resistance, we want to see what happens with the allele frequencies of resistance versus of susceptible. So do the resistant alleles just keep going up and up and up, or do they crash out of the system? If they crash out of the system, we would infer, even with no treatments at all, if they just go away on their own, we can infer that there's a fitness cost, right? So we don't know if that's just differential reproduction, longer gestation periods. Something is different in those resistant mites compared to susceptible. However, we also may see that there is no change. Maybe they just maintain at the same frequency that we started at, so there's no real deviation. However, the third outcome here is that what if we see the resistance alleles increase in frequency over time without any chemical intervention? That would tell us that there is a potential fitness advantage in those mites. And that can happen because when we did some of these tests in houseflies, when I was doing my graduate work, we found out there was this one specific mutation that provided resistance to pyrethroid insecticides. And pyrethroids we use to control Varroa mites, it's apistan or talfluvalinate. When houseflies were resistant to pyrethroids with this one specific mechanism, they actually had a fitness advantage over the susceptible ones. So they just increase. So there was an advantage. So you have three potential outcomes here: a fitness cost, no cost, or an advantage. So that's what we want to find out this year, because that's going to really infer how we manage this mites. Can we, if there is a fitness disadvantage or fitness cost, can we take advantage of that through management in order to knock them down even further?
And if it happened the opposite, what are we going to do about it?
Yeah. So that's where I think we're going to have to rely more heavily on rotations if there is an advantage, because that's what's going to be really important, is that if they keep going up and they have an advantage, we have to find something. So we have to probably do more mitocidal rotations in order to take advantage of that, because we probably will have a harder time getting rid of those with just straight up management. So when I'm talking about management, I really am starting to see a lot of data showing that the importance of brood breaks, how important they are for reducing Varroa levels. And so typically in the north, where they have that extended brood break, they come out of winter usually, not all the time, but usually with less Varroa, because the Varroa don't survive on the adults. However, down here in the south, I mean, we get maybe 3 or 4 weeks where we get just a little patch of brood. So we never go completely broodless down here. So that's why I think that there's definitely something that we could take advantage with management by using brood breaks and that overwintering natural brood break in order to really knock down Varroa. That would be really beneficial, especially in this situation where we have a fitness cost. So we can use management to help us out.
Frank, well, we're going to have to change a little bit the subject, because this is embedded in my mind. I feel that we are in an endless cycle. How we get rid of this cycle of chemical and the Varroa change and the chemical? How we get rid of this cycle? Do we spend time thinking about that, or you're just so focused on your project that sometimes it's hard to get out of the box?
Yeah, no, I don't want to do this Amitraz resistance work.
I know.
I think that we're at the point where we know it exists, we know it's a problem, so we have to really pivot here. We have to definitely, if we want to keep using miticides, we have to stop relying on everybody just using Amitraz. We have to do some rotations, right? Other thing we need to do is start exploring other IPM measures. The biggest thing that we've been finding out at the lab, a project that was started maybe 25 years ago, is using resistant stocks. I came into beekeeping 10 years ago. I've only used resistant stocks with the bees that I raise at the lab. That's all I know. And it will blow my mind how we could get colonies with zero Varroa without any miticide treatments. And yes, you heard me right. Zero mites in the adults.
I know.
Zero mites in the brood. It can happen. It's just that they need the good genetics for Varroa sensitive hygiene. And so because of that, so a lot of my research this next 5 years is going to be looking at how to get people to rear their own Varroa resistant bees. So we have methods to do it. So John Harbaugh and Jeff Harris, they created the way to inspect brood frames in order to score them as resistant or susceptible to Varroa. And it takes a lot of work. You have to look in the brood. You can't just do mite washes. So, and I love it in their paper, they even state that just using Varroa washes will not give you there's very little heritability to the number of Varroa on the adults. You have to look in the brood. That's where there's a higher heritable component. They even say just using mite washes, you're not going to make much progress. So you have to look in the brood. So that's definitely the gold standard, and we know it works because that's how we got Paul line in these VSH, Varroa sensitive hygienic stocks. However, there are other ways that we can do the breeding. So Ariane Avalos, the geneticist at our lab, they're working on a data set where we can do marker-assisted selection for VSH. So we can just get some bees, do some DNA tests, and say if they have these certain genetic markers, there's a very high probability that they also have VSH. By doing that, we don't have to wait for the fall to do the brood inspections like with the Harbo test. We can maybe do 2 or 3 or maybe 4 generations per year. So make a lot further progress on that. So marker-assisted selection with genetics. Another way we're going to try to do this is with Kara Wagner. She has that UBO test where it's this unhealthy brood odor, UBO, that when applied to the brood comb, if they have the higher levels of VSH they have, typically they open up or uncap more of those cells within 2 hours after application. We know that there's that association between the UBO application and capping and VSH. But what we really want to test is, can we use that as a marker for VSH? So again, we can maybe do more rapid evaluation of colonies. So using those methods, we're going to try to get people to look in their own stocks to find the ones that have that behavior and then breed from it. That's the thing with VSH, is that once you know what you're looking for, it's actually not that hard to identify breeders. So when you're looking at when you're in Queens for your own operation, you're going to obviously look at, frames of bees, honey production, overwinter survivorship, all those things that are pretty easy to score. Scoring VSH is a little trickier, but it's just one more trait you'll evaluate when identifying breeders. So that's going to be a project that we're going to work on. So we have people lined up. We're going to do this over the next 5 years, and hopefully we see an increasing trend of colonies in their operations that meet the standard for high levels of VSH.
That's great news. That excites me more. I don't want to say that the work you're doing right now is not important, Frank, but, if I need to pick one, I'm more excited about get out of this chemical and the endless cycle of chemicals inside the hive. I think I'm getting too old. It was, in the past, you heard this, there is a new component or some problem. The beekeeper just waiting. The bee's going to take care of that, Mm-hmm. And it always happened, and never happened with Varroa so far. Maybe we thought we didn't wait too long, or there is other factors involved. But I want to see that back, that the bees are fine by themselves. Okay, mm-hmm. That's what I want to see.
Yeah. And so I think what's really interesting is with this is that, like I said, no chemical interventions, no unique management. Yeah, we have that VSH, and you think about it on a cost savings basis of not having to apply miticide, not having to pay somebody to apply it. So you can think about how much more beneficial. It's probably also a lot more sustainable. I think that the ability for Varroa to develop resistance to VSH is very, very low, I think. So, we're not going to have to go looking for VSH resistant mites anytime soon.
Yeah.
So, yeah, I like this idea of using resistant stock.
Good. Me too. Frank, this is all good news and good research. I want to say thank you for the USDA, for you guys, for the hard work you guys do. I know a lot of times, there is there's so many different projects. There's so people sometimes not aware of the amount of work that the USDA bee labs do. All the labs combined, the Beltsville, the Baton Rouge, and all of them. And I just in the name of the beekeeping community, I want to say thank you for the hard work you guys do.
Thank you. It's a pleasure working with beekeepers, and nothing makes me happier than going out and working right alongside people. I don't like sitting down at my computer. I want to get out in the lab, in the field, and do some real work. I love real beekeeping in the real world.
Frank, do you have any message to the people out there? Do you need anything from beekeepers? Do you have any message for the people?
Yeah, so I think it's really important to not think of miticides as your Varroa control program. You need to start thinking about resistant stock. You need to start thinking about using propolis, we're doing a lot of research on propolis, that we have some data that show that, yes, propolis can reduce Varroa levels as well as all the other.
Wow, wait, what? Stop right there.
Yeah.
Have this conversation because I like propolis more than honey. So I'm a big proponent of propolis myself. And now you're telling me there is this data somewhere and I'm not aware of. Where is
It's coming out soon.
It's coming on.
It's coming soon. We just finished we just did a small project this past year. Maggie Shanahan, one of Marla's Vivek students, just published a really nice paper that we were on as well about how propolis can be used to stabilize, especially EFB in the colony, reduce the incidence and detections of it, but also to do some really interesting things with reducing virus levels across the board. So not just deformed wing virus, but just many different viruses. But one of the things that was in her paper was that we saw a potentially a reduced amount of Varroa in those colonies with high levels of propolis. However, it wasn't probably biologically or beekeeping relevant to beekeepers because it was less than 1 mite per 100 bee that we were finding. So the difference between 0.9 mites per 100 bees and 0.6 mites per 100 bees probably is going to really dictate colony health outcomes. So what we wanted to do is look at different stocks of bees to see if the genetics matter, because with Pauline and Russian bees, we know it's always going to keep the Varroa mites low. But then we also purchased some Varroa susceptible queens. And what we found was in the resistant stocks, that didn't really affect the Varroa levels. They were able to keep Varroa levels low, whether they are high or low propolis environments, just because Russians and Pauline are good at keeping Varroa levels. However, in the susceptible stocks, the Varroa infestations were dramatically lower, and not a few percent. I'm talking like 5 times lower in colonies that had high levels of propolis. So there's a couple things that might be happening here. One, we think that propolis has some kind of compounds in it that kill mites. So whether what they're foraging on, what that propolis is consumed of, may have miticidal properties as well. There's been some other lab work that show that might be the case. The other thing that we've been seeing, and I hope this is the mechanism because it's not as exciting, but this might be the case, where the propolis might have some insecticides in it that can kill the mites and not harm the honeybees, be less bioavailable. So we've done pesticides in propolis. Yes, there are a lot of pesticides in propolis. There's no way around it. However, in the case we're looking at for mites, it might actually have a benefit by reducing mite populations. So there's still a lot of work that we have to do in this area. So we're going to reproduce that experiment at a larger scale this year, and with new propolis boxes that we're going to, and then also now we actually have methods for doing, what's the word I'm looking for? Less burdensome pesticide residue testing from propolis. Well, we did this with the Gastonia lab, and we sent them a bunch of samples. They said, "Oh, do you plan on doing any more propolis research?" We said, "No, not really." They said, "Well, good, because we're not growing it anymore because it harms the machines." So usually they send other things to machines. They could get a couple hundred runs. But with propolis, they were getting like 5 or 6 runs that they had to do maintenance. So
I know exactly what I tried myself, and was a mess to clean the machine after.
Yeah, so yes, it was creating a backlog. So it was difficult, but we do work. We have worked on a new method to potentially get it through to do pesticide residues without really affecting the machine. So yeah, we hope to look at that a little bit more.
That's very good news. I'm excited to see that kind of research because from my personal experience in Brazil now, I know 80% of the beekeepers in Brazil do not treat for any, and we have the Africanized bees there that propolize everything. Sometimes it's even hard to open the hive, And I always find always thinking maybe propolis has something to do with Varroa too, or any other things, or maybe affecting the virus load, and so the Varroa itself is not causing too much damage because the viruses are down. And I always, hypothesizing a lot of things and waiting for data. And now you bring me this data in my face right now like that. Come on, man.
Yeah, no, we're gonna write that up very soon. We think that we have enough data to publish it as is, and then we'll follow that up with a more extensive study. But the interesting thing I'm really interested about the propolis is that studies is that, as you just mentioned, Brazilian propolis is different than propolis that we have here in Louisiana. Yep. Very, very different. And that's to be different than what's up in North Dakota and New York and every other place, right? So it gives us a lot more chance to explore the propolis terroir, as you would say. To see how different components of propolis might be contributing to this as well.
That's a lot of work. And I know for a fact, I grown up with Brazilian green propolis. My mom made her own recipe for my wounds or my throat. And when I tried the propolis that I found here, never worked with me, at least, for the things that I'm used to. So I decided to make my own. So I bring my own from Brazil. I have a stock here. And so I know how different propolis at different locations, just like honey. Honey is kind of different a lot from different locations. Propolis the same. I think the goal now for the researchers is to find a specific compounds or combination of compounds that do the job, so we can maybe produce them in large scale or learn more from them to use those new knowledge in our benefits here. So great. That's great news, Frank. Thank you for the information, man.
Yeah, a little sneak peek. So yeah, that's what we're going to be working on this summer as well. So exciting.
Well, we will invite everybody now over there to come here and explain the story much better now when the time.
Yeah, you'll have to have Mike Swarty Finchner come on and talk about propolis. So that's work that we've been collaborating on with. So yeah, I've come around to the benefits of propolis for many, many years.
Yeah. I think people are expecting that, and I bring him before to talk about propolis, and was one very well accepted video and episode of the live stream. I think people is waiting for more, so that's great news.
Yeah, there will be more for sure.
All right, Frank, do you have any other message for the people out there? Something? Yeah, are you going international with this test? What's going on with that?
So we've been talking to Canadian beekeepers about this. They've been reporting a lot of control failures the past few years. So I talked to them a lot, the Alberta beekeepers, especially. So this is something that we've been talking about, and this kind of become the resistance test in the field is kind of becoming universally used across many, many different places. It's really important to make sure that we're all doing the same tests. That way we compare results, kind of apples to apples kind of thing. Been working with Joel Gonzalez Cabrera and his group over in Spain, especially on the genotyping studies. And so that's definitely been a big thing. So it's definitely worldwide. Now that we have Varroa in Australia, it's applicable everywhere else. Other things that we're going to be doing, we're following up. When we were doing the genomics of Varroa before, I mentioned with Ariane Avalos at my lab, we noticed that there's some potential shortcomings of the Varroa genome. So we're probably going to be doing a Varroa pan genome. So we're going to get Varroa from all over the world, sequence them, and then try to make a better reference sequence. So
a different 2.0 assembling kind of thing.
Yeah. Just because with honeybees, we know that the reference genome isn't representative of most honeybee stocks. Actually, Garrett Slater is one of Ariane's postdocs, and he has some really interesting data coming out about the honeybee pan genome. That a lot of the honeybees aren't, a lot of the reads aren't mapping, or they're just not consistent with the other one. And they have some really great figures that show the improvement in mapping when aligned to the pan genome compared to the original reference. So that's pretty exciting. It got me too excited. I said, "Oh, that looks great for honeybees. What can we do? Can we do that with Varroa?" So that's what's next.
It is very exciting for the research perspective, to have the different assembles and different strains and different genotypes. Cool. Just like the honeybees and the human genome, always evolving the assembling and the differences, so we can use that information to our advantage.
Yeah. Cool. So the future of resistance monitoring is definitely the genetics. So we're collecting Varroa from all over the world, and then also too going back in time, seeing if there's anything in the freezers. And so I did find out a motherload of old Varroa samples. I got some from all over the world collected in the 90s. So we need to genotype them and see if there's any difference between old Varroa and contemporary Varroa, how they've been evolving. So going to be interesting.
That's easy if it's already in the freezer.
Yeah. I just stumbled across some really great samples. So yeah, it was like Santa Claus came and delivered a present for me.
Yeah. All right, Frank, if you don't have any other message to people there, I want to say thank you for your time. one more time, again, thanks for the great work that you're doing and all the people at the Baton Rouge lab and the USDA in general. Fantastic work, and opening a lot of doors for the beekeeping industry to take advantage from. So thank you in the name of the beekeeping community.
Well, thank you for inviting me, and have you back next year when we come up with all this new research on Propolis. So.
Definitely. I'll bring you back for sure when you have more results for us. All right. That being said, thanks again. And for you guys at home, this is going to be available for you not only here on YouTube, but also in Spotify and all podcast platforms that you are accustomed to listen to your podcast. That being said, thanks for watching Inside the Hive.tv, the show about bees, and see you guys in the next week. Bye-bye.